Alright guys, as promised, here's the first video looking at predicting products with synthesis and decomposition reactions. So just kind of review a little bit on reactions. There's several things to keep in mind while we're doing predicting products. First off is the states and matter. Remember, with elements, the states and matter can be identified with the periodic table. This means the color that the elements are. Remember, if it's black on the periodic table in the classroom, it's a solid. If it's red, it's a gas. And if it's blue, it is a liquid. In terms of compounds, remember, ionic compounds that are not dissolved in water are solid. Most covalents are either gaseous or liquid depending on their size. And then from there, you'll be told otherwise, whether it's dissolved in something or not. So if it's dissolved, remember, it is considered aqueous. Remember the diatomics that we talked about in class a little bit today, which is hydrogen, nitrogen. Here, let's write those down. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and of course iodine. And there are some similar ones. For example, sulfur appears as S8 in nature, and phosphorus appears as P4. You do not need to have those memorized, but I would be able to recognize them. As always with reactions, you need to be able to balance them. You'll need to have a basic understanding of the solubility rules. So one nice thing about the new test is you don't have to have them memorized, but I would still know some of the basic ones, like your alkali metals are always soluble, your halogens are soluble except with some of the heavy metals like silver, mercury, and lead. This does not include fluorine, etc. You may want to see if you can pull them back up from when you did them in regular chemistry or honors chemistry last year. Otherwise, you can see them in class when we do double replacements a little bit later. Activation series, again, you don't need to have this memorized, but be able to use it. I'll show you how to use that in class. And then, of course, net ionic equations, which we'll talk about tomorrow's video. So with synthesis, don't make synthesis more complicated than it needs to be. It's just taking two or more elements or compounds and then combining them so that there's one on the product side. If there's only one product, we're dealing with a synthesis reaction. Now, I make it a little bit more complicated than it needs to be, but it does not need to be complicated. The 8 basic types of synthesis reactions, in all honesty, a metal combining with oxygen is the same thing as a metal combining with a non-metal. A non-metal combining with oxygen is the same thing as a non-metal combining with a non-metal. We really don't need to have these separations, but we do just to kind of give us that idea. So 1 through 4 really aren't too bad. 5 through 8 require a little bit of memorization in terms of the products that are formed, but again, not too bad. So let's take a look at these. Okay, first one is the metal with oxygen. Basically, all you're doing is combining a metal and a non-metal to form an ionic compound. Okay? One of the reasons we separate this is because oxygen reacting with anything is a combustion reaction. So aluminum reacting with oxygen is combustion, though it's not our combustion we're used to seeing with carbon dioxide and water. That's an organic combustion. What we're looking at here is a general combustion. Anything reacting with oxygen is combustion. So that's why it's kind of separated here. But really all you're doing is a metal plus a non-metal forming an ionic compound. So not too difficult, we just need to keep charges in mind. So here, potassium, which is a solid on the periodic table because it's black, plus oxygen, which is O2 because it's a diatomic and it is a gas, reacts and forms potassium oxide. Well, potassium's +1 in its ionic state, oxygen is -2, so our compound is K2O. And this is an ionic compound, no water present, so it is solid. We'll worry about balancing a little bit later. Okay, copper, we know is Cu. It is a solid based off the periodic table. Again, oxygen, O2, gas. With this one, notice this is a little bit more challenging because we don't know if we're forming copper 1 or copper 2 oxide. In most cases like this, unless they tell you a charge, we assume it's the most common charge. And in terms of copper, the most common charge is a +2. So we're going to form copper 2 oxide, copper 2 meaning copper +2, and oxide being -2. So our compound is CuO. And again, no water, ionic compound, must be a solid. So pretty simple for the most part. Okay. Nonmetals with oxygen is a nonmetal plus a nonmetal. You are forming a covalent compound. Now, covalents are a little bit more challenging because we don't have a name to work off of like we're used to, like here, carbon dioxide to work off of, nor do we have charges. So really the best we can do is take a wild guess with the most common compound we're used to seeing. So for example, sulfur, notice I have S8 here because that is its elemental form. And this of course is a solid based off the periodic table. Reacts with oxygen, which again is O2. Gas, again this is a combustion, just with a non-metal instead of a metal. Well, the most common form of sulfur and oxygen is sulfur dioxide. So SO2 is our compound here, and sulfur dioxide is a gas. It's a small covalent compound, which typically are gaseous. So not terrible, a little bit challenging to some extent. Let's move this up so we can see it a little bit better. The next one works similarly. We have nitrogen, which is a diatomic, N2, and it's a gas, plus oxygen, which is O2, again, gas. Now, nitrogen and oxygen, there's several common forms. One of the most common would be N2O or N2O4, and it doesn't really matter which one you do. I'm just going to do N2O for right now. And of course, this is a gas, again, light covalent compound. The one nice thing about the covalent compounds being formed in predicting products, a lot of times on the rubric for these types of problems, they would have 2 or 3 different answers that they would have accepted. So there's not necessarily one right answer, but it's one that makes most sense. So in this case, SO2 makes the most sense with sulfur and oxygen, and then N2O or even N4O2 would work as well. Either way. Okay, again, ionic compound here, metal, non-metal, forming ionic compound. So we have strontium, Sr, solid, plus nitrogen, N2, which is a gas. Really no different than the metal with oxygen, except we just have nitrogen here. So when we put strontium, which is a +2 charge, with nitrogen, which is a -3 charge, we are going to get Sr3, N2. It's ionic compound, no water present, must be a solid. By the way, these charges, I'm hoping we know that this comes from the periodic table. Strontium's in our 2nd period, so it is a +2. And nitrogen's all the way over in the 5th period in terms of the representative group, so it is a -3. So again, we would have a -3 up here, +2 up here, and we would cross and swap to get those numbers. Okay, again, copper, solid, plus sulfur, which we're going to make it our S8, solid. Again, copper, we're not given a charge, so we assume it is its most prevalent or most common, which is +2. So copper is +2, sulfur -2. We have CuS, and again, solid. And yes, you'd have to go back and balance it. Okay. Same with our non-metal. We are again forming a covalent compound. And again, you just kind of have to take the best guess you can. In this case, carbon, solid, plus sulfur, S8, solid. When these two combine, CO2 is the most common with carbon and oxygen. Well, guess what? Carbon and sulfur is CS2 as the most common. And again, there would be multiple answers that could be accepted depending on the situation. Now in this case, this really is the only formation of carbon and sulfur we're going to have, because carbon cannot hold more than 8 valence electrons due to the fact that it does not have a D shell. And this guy here would probably be a gas, considering the fact that it is a light organic covalent compound. But it could be a solid. We would have to get more information on that one. Again, same thing down here, boron, which is a solid, plus hydrogen, which is H2 and a gas. Now, think back to what we know about boron. Boron can only hold 6 valence electrons, which means it can only form 3 bonds with hydrogen. So our common one here is BH3, and this is going to be a gas. So again, covalent compounds, ionic compounds, not too bad. Let's look at some of the ones that are maybe a little bit more complicated, where you actually have to kind of memorize what's going on to some extent or another. When we have a metal oxide, like magnesium oxide, and water put together, at first it looks like it could be a double replacement reaction if we kind of ignore our products that are here. Thing is, if I switch magnesium and hydrogen's place, I end up with the same exact thing that I started with. So that doesn't make a lot of sense. Or even if I took the hydrogen out and threw it with the magnesium, one hydrogen out and threw it with the magnesium, it doesn't make any sense. So we have to kind of look at this and go, okay, it looks like a double replacement, but the pattern doesn't make sense, so this is something different. When you have a metal oxide and water reacting, they're forming a metal hydroxide. So it's not double replacement like it looks. It is a synthesis reaction. So let's go down here. Potassium oxide, K2O. It is a ionic compound. No water present to begin with, so it is a solid. It is reacting with water, H2O, which is always a liquid, unless we're told otherwise. With that reacting, we know it's going to form a metal hydroxide. Well, that's going to be potassium hydroxide. Potassium's a +1, hydroxide's a -1, so KOH. And you really don't need the parentheses here. I just went ahead and put them on here. Now, water is present. Chances are it will be in excess. So this guy's going to be aqueous. Okay, same thing down here. Zinc oxide. Notice there's no charge here. That's because zinc is always a +2. So we don't need to baby ourselves with saying zinc 2 oxide anymore. Zinc oxide we know is +2, with oxide being -2, so ZNO. And that again is a solid plus water, which is a liquid, reacting to form zinc 2 hydroxide. Again, zinc hydroxide, we don't need the 2. Well, Zn +2 plus hydroxide -1 is OH2. And in this case, our hydroxides are not very aqueous, so chances are this guy is going to be a solid in terms of solubility rules. And we'll worry about solubility rules a little bit later. Don't worry about them right now. If you didn't know that was a solid or this one was aqueous, that's okay. Just get the basic pattern for now of being able to write them. Okay, so that's a metal oxide in water. Let's look at a non-metal oxide in water. This one's maybe a little bit easier to look at. Again, we have this weird pattern where it looks like it could be a double replacement because we have 2 compounds to begin with, but again, the double replacement doesn't make sense. Hydrogen and carbon switching places doesn't make sense. It also doesn't make sense because both of these are covalent. In a lot of cases, double replacement reactions are only going to occur when we're dealing with ionic compounds. Okay, well, neither one of these are really technically ionic. So we're dealing with another one of those patterns that doesn't make sense. And what happens here is we end up forming an acid. And this one's a little bit more complicated. A lot of ways to help you remember this is you just literally add the 2 together, and that gives you your acid. So let's look at an example. Sulfur dioxide is SO2. It is a gas in most cases, plus water, which is a liquid. Well, if I add sulfur dioxide plus water, I get 2 hydrogens, because remember the hydrogen always comes first in the acid, 1 sulfur, and 3 hydrogens, or 3 oxygens, I'm sorry, 2 from here, 1 from here. So our acid is H2SO3, and it is aqueous. Okay, same thing down here, sulfur trioxide. Again, probably a gas. H2O is a liquid. Okay, again, if I add this up, 2 hydrogens, 1 sulfur, and 3 plus 1, 4 oxygens, and again, aqueous. Now, our nitric acid doesn't work quite as nicely. We can look at one of the nitric or nitrous acids tomorrow in class. But that's kind of the basic gist of a nonmetal with water. Okay, again, something we just have to memorize is our metal chloride and oxygen. In this case, again, it looks like a single replacement reaction, but it's not. In this case, it is a synthesis where we're forming a metal chlorate. So, magnesium chloride plus oxygen is going to form magnesium chlorate. Well, magnesium is MgO2, or Mg plus 2, and then chlorate is ClO3 minus 1. Because it's -1 and magnesium's 2, it's MgClO3 2. Same thing with aluminum chloride. AlCl3 plus oxygen is going to form aluminum chlorate, AlClO3, parentheses 3. Aluminum plus 3, chlorate is -1. Okay, and last one is metal oxides with carbon dioxide. Again, looks like double replacement, doesn't make sense because of these oxygens can't switch places without causing the same thing. So in this case, we're forming a metal carbonate. Okay, calcium oxide plus carbon dioxide is going to form calcium carbonate, which is CaCO3. Okay, that's all the time I want to do because we're at about 15 minutes. Just so you know, decompositions are exactly the same, except they are the reverse. And we'll leave it at that. Just see what you can do. Here's a couple practice problems if you want to look at them for decomposition. Okay, and we'll talk about them tomorrow in class. Thanks, guys. Have a good one.